All right, well, maybe we'll wait one more minute because we don't seem to have very many in-person people. Uh, if you know anyone who's in person, tell them to come soon. Yeah. All right, so maybe we should get started. So, yeah, welcome everyone to, there's going to be people entering the waiting room. All right. Well, yeah, so welcome again, everyone, to lecture 8 of CS 545, the introduction to robotics. So for today, what we'll do is we'll finish up the remainder of the Kalman filtering from the last class, and then we'll move on to the particle filtering, which is another alternative filtering algorithm that has other trade-off and advantages, the disadvantages compared to the Kalman filter, all of which are under the general algorithm framework of tracking the state or estimating the unknown state of some environment or the robot given sensor observation from reading that we get directly. And yeah, I guess the other logistical things are lab 1 would do yesterday, so hopefully that went well. I mean, I can tell that like by the number of views that more people viewed my lecture where I showed the ROS running. So I assume a lot of people were looking at that to see if they could reproduce it. Because there's like a spike in the viewers if you plot them. And homework 1, the regrade requests are due today. So if you have a regrade request, put it on Gradescope and we will get to them. But we can't accept regrade requests after the deadline. Otherwise, at the end of the course, we would just be overwhelmed by people asking for another point if they think they're like, like a half a point within the next grade threshold. So, and yeah, homework 2 is out and will be due, I think it's next week. So I hope that's going well. And yeah, any other logistical questions? I have the Google Doc open and I think I don't remember how many people there are on Zoom, but if people on Zoom, if you have questions, just type it in the document so that I'm not too distracted by different things. Uh, all right. Well, so I guess we can move on to the technical portion for today. So if you remember, we were talking about Kalman filters, which are an example of a Gaussian filter from last class. So if you remember the general filtering approach, we have our control, like what the robot was doing. And then we have VT, that's like some sensor data. So, maybe it's a camera, maybe it's from a GPS or whatever. It gives you some observation. Now, for Bayesian filtering, if you remember, this thing was just belief. So it was like some distribution, maybe like a discrete distribution. The key assumption of the Kalman filter is that we can represent this as a Gaussian. So we just need a mean vector and a covariance matrix. That's enough to specify our belief. All right, more people entering. Cool. Yeah. Well, we'll probably get more of the people asking to enter. So I'm just gonna leave this open. Yeah. And then again, the Kalman filter, so it's a recursive algorithm. So it's like all the recursive algorithms, they take in whatever we computed at the prior time step, incorporate our action, our measurement to get the next thing. And the next thing here is just the next mean vector, the next covariance. Because again, these two ingredients are all we need to specify our belief, assuming we are using Gaussian, assuming that we make assumptions on like, the measurement and the dynamics are linear with Gaussian noise. So if you're doing a robotic problem and you think that assumption doesn't hold, then you probably shouldn't use a Kalman filter. But if you think it does hold, if you have a good reason that it might be useful, then of course, maybe the Kalman filter is a good choice. And yeah, so I think we left off like roughly speaking that with this diagram where, we have our like an initial belief. So this is like some kind of graph that shows a Gaussian, so it's like a bell-shaped curve in one dimension that shows our belief of the robot. So like the robot is in some long corridor. It doesn't know its position exactly, but the sensor will tell us, we think the position is centered, where the peak is highest with some variance. Yeah. So here the covariance matrix is just one thing. It's just like the variance. But in general, this would be for higher dimensions. It's just one dimension so that we can like actually visualize it. And then, the key idea is that as we incorporate measurements like for B, we get a new sensor reading that says, well, maybe the robot is here, like roughly here with some estimated variance. And then our new belief should be shifted so that it like more closely matches the observation. Yeah. So like that's the intuition and the context for the Kalman filter. Yeah. So, we talked, I did mention things like, if you don't have a Gaussian, maybe you shouldn't use a Kalman filter. Now, there are some cases when these types of filters are still used, even when we don't have a Gaussian, or even if we don't have like exactly a linear system assumption. So there, to some extent, you can still use Kalman filters, but you have to adapt it in some way in order to approximate it if we think our like dynamics are not actually linear with Gaussian noise. So if you want to relax the assumption, then maybe our state transition function uses a nonlinear function g. And the measurement probability uses nonlinear function h. So like epsilon and this delta, they're still like noisy terms. So here we're gonna again assume that they have some, some Gaussian noise, but we're not gonna assume that there's a linear aspect. So we assume that G and H, they can be whatever. So if you remember before, we had like this thing was basically our dynamics. It takes in, like prior mean plus the action. Yeah. So here we don't have that. It's just this arbitrary function G. So we gain more generality, like this can be used in many more cases, but if this is an arbitrary function, then there's not really that much we can do about it. Like it could be whatever. So yeah, before we get to that, I think we also wanted to talk a little bit about the linearity assumption. So if you look at the textbook, they show these types of figures a lot where it's one variable like x to the bottom right, and then there's another variable to the top left here, that's y. And I think the purpose of this figure is just to show, have a little more intuition about what it means to transform variable from one to another. So if you look at this variable x, and then you have a transformation function here, which is y equals 2x. Then if you look at like where the dots are at the bottom, and you sort of push them up, you can like you put them here where it intersects this line, and then that becomes a horizontal line to match some value of y, right? So here x is going from -3 to 2, and then y is going from -3 to 2 here. Yeah. And I think the intent of this figure is also to show that when you transform this, this PDF of variable X by this function, you still get something that looks like a Gaussian, right? If you tilt your head and then you look at, the PDF of Y, it still looks like a bell-shaped curve, symmetric, centered at some value. I think it's 0 here. Yeah. Yeah. So this is an example of what we call a linear transformation. So if you have a nonlinear function like y equals x squared, then one way to think about it is that when you have different points of x, and then you pass them through the function, their spacing will change as you plot them by y, right? So the spacing between like 0.1 and 0.3 is going to change. And then the spacing for these two, these two will get, I guess these two will get relatively closer to each other from here. Yeah. And if you notice that the function here, the PDF of y is no longer a Gaussian, it's not symmetric around some value anymore. So yeah. So again, hopefully this, I guess the context here is just to think about, what does it mean when we try to pass in a variable and then transform it by something, by some function. And if you look at the textbook, you'll see a lot of the diagram where they have some variable x here, some usually nonlinear because it's more interesting that way, like some nonlinear function, and then you plot some newer density. Yeah. All right. So, all right, so going back to the linearization thing. So we assume that our state transition and our measurement probability, they have some noise, but they're now using nonlinear function G and H. And so the key idea of what we call the extended Kalman filter is to approximate G by a linear function. And the motivation here is that if we approximate G, or H for that matter, then the mechanics basically reduce to that of the normal Kalman filter. It's just that we're approximating things, of course. But if we turn G and H into linear function, linear approximators, then we have linear function, we can just use the Kalman filter. Yeah. Does that make sense? Of course, how good of an approximation this is depends on how close G and H are to actually being linear functions, right? If they're completely crazy functions, then the linearization is going to be a very bad approximation. But the key idea is if it's close enough to being linear, maybe we can give it a shot. Yeah. Does everyone know how we actually approximate function as a linear function? What techniques do we use? It's a very general thing. So yeah, everyone's seen the Taylor's theory before. Just checking if everyone did. So a first order Taylor expansion of some function like this. So this is some weird shaped function, right? If you consider some point A, then you can make a dashed line to see what the function value is at A. And then the Taylor expansion is it's a linear function that is tangent to the original function at this point, right? Because if you look at where it's like the same, I got the same slope when you try to imagine the function here expanding out linearly. Yeah, so hopefully everyone has seen the Taylor series expansion. So it basically means that if you have some function f, then you can approximate it with f of a. So it has the approximation has to be centered at some point. What that point is another decision-making thing, but here we're just assuming that we have a, right? And then you add the derivative of the function f at a multiplied by x minus a. So, yeah. Right. And so what we do here for the extended Kalman filter is to do linearization on G as well as H. So G and H were those arbitrary functions that we just now assume describe our state transition and the measurement probability. So, or measurement or observation probability. All right, so let's look at what this means. This is our assumption. So we have xt, like the next state of the environment or the robot is equal to some function g given the action that the robot took and the prior state plus some noise. Now we're going to consider the derivative of that function with respect to xt minus 1. So if you're wondering, well, why there's two arguments here, right? Ut and xt minus 1. So ut, we just assume that like we know because we commanded or the robot commanded itself to do something. And so I guess the intuition is the interesting variable here is xt minus 1, especially because that's the thing we're trying to estimate. So we only differentiate it with respect to the xt minus 1 part. And if you look at what's going on here, this is basically our linearization, right? So you have G of our standard input. It is approximately G centered at the mean. So again, if you look carefully, it's UT and mu t minus 1. So this thing is the mean state from the prior time step. Multiplied by this Jacobian matrix. And then you have this other term as well. So the reason for this is that, if you have xt minus 1 minus mu t minus 1, you get a vector minus a vector. So you get a vector and then need a matrix here so that you still get like a vector to make the dimensions all work out. Like in code, you would have to check the shapes of everything to make sure it works out. So yeah, that's basically what happens here. And what we get from this is this arbitrary function g is equal to this g plus this matrix multiplied by this vector. So we get like some vector plus matrix times vector. And so in some sense, it becomes like a linear function. It's like a linear function now. Except again, there is an approximation. So how good it is depends on whether g is actually a linear function in most of the input space. Yeah, hopefully that intuition is kind of clear. Like we're trying to get the Kalman filter strength, but without actually requiring that g be linear, because that's a very strict assumption. And if you remember last class, so we did a lot of exercises where we had to give you like these formulas, and then we told you like write out the Gaussian, like what is the probability of this thing, or like what is the density of this thing? Yeah, so that's a common exercise that we did last time, and I'll do it just this time. So if you look at like what is some like the probability of xt given the prior action and the xt minus 1, it is a Gaussian with some normalizing constant. So if you really don't like how it looks like, just put in like your eta, and then that just gets rid of some of these terms. Time the exponential function. So you have this whole exponential with all these things in the bracket. And you have your -1/2 because every time we do a Gaussian, you need like -1/2 there. And the reason for why it looks like this is that xt is the variable that we're interested in. So like every time you have this here, you have to repeat it here, and then this whole thing becomes the mean, the mean vector, right? So the mean is g of the action and the prior mean plus this term, and then you just copy that here. And then you repeat it on the other side, then you stick in the inverse of the covariance here. And again, we're assuming that epsilon follows a zero mean Gaussian with covariance specified by RT. So it's time varying, but if you're modeling a problem and you think that the noise is the same over time, just get rid of that T notation. So, yeah. All right, any questions on this? The Google Doc is quiet today. Yeah. All right, and then one more linearization. So we did a linearization of the function g, which is for the transition probability. And then we also do a linearization for the measurement. So remember that we had vt equals some arbitrary nonlinear function h of xt plus some noise. So imagine this is like some GPS sensor that is supposed to tell you, this is our observation of the underlying state that we don't know exactly, but we use our sensor to estimate. And then we have a linear approximation again. So, it's basically the same as what it was the last slide. I won't go into too much detail. It's basically, you again have the linearization at some point plus some covariance matrix multiplied by some vector. Yeah, so here we're using mu. So mu again is the mean state, because usually when we talk about linearization, it's a good idea to linearize at the mean value. I guess because under the assumption that most of the value accumulate near those are the most interesting parts of the function to look at. Yeah, and then you can also write it as a Gaussian. So you basically get this. So again, you have your probability of ZT given XT is approximately this normalizing constant. Again, you can just write it in eta if you really don't want to write all this out. And then you have the exponential with -1/2, the value of interest, minus the mean value here. Yeah, and then now Q is the covariance. All right. All right, so to summarize sort of like the Kalman filter versus the extended Kalman filter. So again, these are algorithms for estimating some state, right? And here the state is represented with the mean vector and the covariance matrix. So that's like how we represent things. That's all the information we need to know to specify the state of the environment. And the main difference is with G and H. So we have mu t, which is this linear function. You have matrices A and B, but here the mu is just G. Yeah. And so essentially what happens is that you can use your matrices A here, but here you have to use the matrix G, which is the Jacobian that we talked about a few slides ago. But otherwise, like these algorithms are pretty similar. Again, just the minor differences in trying to alleviate the assumption that we don't have a linear function with the extended Kalman filter. Yeah, I don't know why the book has extra spaces here. I just copied a screenshot from the textbook. So yeah, yeah. All right, any question before we move on to an example? I feel like an example might also help out with understanding the Kalman filter. Uh, hmm. uh, all right, so here's an example. So when people give examples of the Kalman filter, a common example that people do is like radar tracking. I think that's actually the history behind why Kalman filters were invented. I believe it was because people were trying to track like radars or something during wars. I'm not totally sure about the history, but I think this is the context behind how Kalman filters were developed. So imagine that we have this setup here. So we have a radar system that's trying to observe the position of a plane. So here's a plane. It's flying at height h with some constant velocity. And yeah, so x is like some distance from here to the place underneath the plane, and then r is the distance. Yeah. If you want to think about the notation, then it's x, like x dot, that's a velocity thing. So we're also going to use, b for the velocity. So x is like some position, and then if you add in the dot, it becomes velocity, and then because the velocity is constant, what's the acceleration? Yeah, so the acceleration is 0 here. The change in the height is also 0 because we just told you that. Yeah. Okay, this is just a simple example. So obviously, if you're using Kalman filters in like wartime or whatever, you would have something more sophisticated. Uh, yeah, so in terms of the dynamics from time t-1 to t, we're going to assume that we have xt is equal to the previous xt of the previous state, or it's really the previous position on the real line, plus your our velocity term times the change in the time, right? So if the change in the time is very big, then you get more distance. Yeah. And of course, if the velocity is very big, then you also get a bigger change in the position. And because we have constant velocity and constant height, then the math for that just reduces to like this. And then RT is the distance at time t from the radar to the plane. So like if the plane is facing this way and it goes this way, then of course the value of R is going to increase. And if you do like trigonometry, you derive it as RT equals square root of xt squared plus ht squared. Yeah. All right. So, all right. So one thing that I do apologize about this example is that the notation can be a little bit tricky here. So when we talked about xt, vt, and ht, like that is the state of the system, right? But sometimes we often use xt to represent the whole state. So unfortunately, so it is a bit confusing, but xt here is really supposed to be part of the state. I'll try to make this a little bit clearer in going forward. So what I want to do here is ask if this vector x with all the terms, this is the state at time t, right? It is equal to something times the state of the prior time step. So you have like the prior state at time t-1. You have a matrix that's like left multiplied. there's nothing there because you can tell that I'm going to ask you like what goes inside. And then you have this thing, which would be the next state. Yeah. So, yeah, one thing, the one question is, of course, well, what goes on in here? And yeah. Whoever is typing in the Google Doc, yeah, you got the first two rows. I think you know the third one. So, yeah. Yeah, so the notation clarification, the state is our 3D vector, like x vt, or in this notation, we also use like x1 comma t, x2 comma t, x3 comma t. So yeah. And what goes inside here is this matrix, right? So we have, like, if you do the matrix algebra, and then you get like x1 comma t is equal to this thing, x1 comma t minus 1 plus this term, which is really the prior velocity. Right? Yeah. So any questions on like what this equation is showing? And are the dynamics linear here? Yeah. I mean, sometimes it can be tricky to say like what does linear mean when we have matrices and vectors, but just think of my intuition of that. Anything that's nonlinear would have some like square root or squares or like different powers in the exponent. So if it doesn't have that, it's probably linear. Yeah. So yeah, the dynamics will be linear. So what about now? So we have Vt is equal to our measurement. Now, our measurement here is the sensor that is telling this value R. Yeah. And so if you punch in the number, you get this thing. It's the same as if you had xt squared, you put that in here. And then if you have ht squared, you also put that there, plus some amount of noise. Yeah, so is this linear? I mean, well, yeah, so I just told you that if you have like some square root and exponents in there, then it's probably not linear. So in this case, yeah, it's not linear. So what do we do? What do we do with a nonlinear function and we want to use the Kalman filter? We just covered it. Okay. Can you speak up, please? First order Taylor expansion. Yeah, so I think you're saying first order Taylor expansion. Yeah, which is what we do. Yeah. And so we will linearize this at the mean value. So usually when we linearize, we linearize at the mean value because like, that's as good as the point that we can get. So if you remember from the prior slide, or if you have like a printout or whatever, then this is the approximation that we were using. And if you do the math, then HT is a Jacobian. Now, because it's the Jacobian matrix, so there's a formula for computing it. And if you remember, a Jacobian is applied. It can be applied if you have like a vector value function. So a function that takes in some vector, then it gives you some other vector, right? Of course, here is like a real value function, but in general, it would be like a vector to a vector. So it's a function from 3D to 1D. So the Jacobian is 1 row by 3 columns. Yeah, so that's why you see like the 3 things there. So if you look at this line, this is just the definition of a Jacobian. So if you look on Wikipedia, you have the definition of what a Jacobian is. We're just plugging in that definition here. And you differentiate the function for at each of the different components. And if you do that, then you know that the square root is the same as taking something to the power of 1/2, and then you pull down 1/2, you get the power of minus 1/2, which means you have 1 over the square root of something. And then you apply the chain rule, and then you get this, basically. Yeah. The derivation here, pretty clear. And if it's not, you can always look at it in your own time. Yeah. I mean, I record the lectures, so. So if we take a step back, what we did here is we have a system that is trying to track something. And the sensor is basically the function h that returns the value of its estimate of r. And there's going to be a true value of r, and then the sensor will give you some estimate, right? So like if you're trying to track a plane, like you're not going to get the position exactly. You really have the position plus some estimate of the error, right? So yeah. And taking another step back, I think one reason why Kalman filters have become popular for certain tracking problems is because, like, when something is moving, you can think of it, you can kind of assume that, you know, maybe if it's like moving in one direction and you have like one main mode of where the thing might be, then Gaussian could be a good assumption. Like you have one mode with some amount of error. If you were dealing with an estimation problem where there were multiple modes, then Gaussian usually are not the best fit for that. Unless you're doing like mixtures of Gaussian, but then we have to add in more things to the Kalman filter to make it work. And we're not covering the mixtures of Gaussian case in this class. Yeah. Yeah, so another thing that you might see is this kind of plot is characteristic of some kind of result that you might get when you're trying to estimate, you know, the range. And then what happens here as time goes on, if the plane starts here to the left, and then it goes straight like this, then it becomes closer when it's like closest when it's like right above here. And then it gets further when you go out. And so that's what this kind of plot is basically indicative of many tracking algorithms where something is far and then it moves closer and then it moves away. So yeah. So like this, I guess whoever made this plot like had some example problem, then they just plotted this here. I think the bigger takeaway for this class is being able to deduce that, if the plane is going from here to here, like how do you actually do a linearization, and what could a potential plot look like? Yeah. All right, so to summarize, if you consider this and the last lecture, so we cover Gaussian filters and Kalman filters, so they represent belief as multivariate normal distribution. So therefore, continuous state. So if you're doing some tracking problem where the state is discrete, like if you have a grid where the state is like one item in a grid, then it's not a good fit. Similarly, if you think you're doing some kind of state estimation problem where there's multiple distinct hypotheses, then it's also not a good fit. And you should advocate for not using a Kalman filter. But if you are dealing with a continuous state estimation problem and you think, well, maybe there's like one main mode where the belief might be, then yeah, Gaussian filters could be a good fit. And you can compute this stuff in closed form, and the calculations are very easy, relatively speaking. So yeah. And coming up next, not next class, but today is going to be particle filters. So we covered Bayes filters, we covered Kalman filters, and then extended Kalman filters, and then the last main filter we'll cover is the particle filter. So any questions so far? Yeah. So hopefully the name particle filter gives you a sense of like what's gonna happen. Yeah, question.
Please just make clarify the formula the last slide. Oh, sorry. So yes. Yeah.
This thing?
Yeah.
Oh, okay, so, all right. I'm gonna do one of them and then you can just do, the other one is kind of similar. Equal. Hmm. I'm already out of room here, but maybe. Uh, uh, so is this clear how I got from here to here? So this is the function h, right? H is the this thing over here. And then you are differentiating it with this thing. So it's the derivative with respect to x1 comma t. Yeah. And then h is this thing to the 1/2 power. So if you have a square root, it's like to the 1/2 power. So if you go from here to here, it's just like whenever you take a derivative, you pull the exponent down, like the 1/2 goes here, and then you subtract 1, so it becomes -1/2. So you get -1/2. And then this is the chain rule. So remember that whenever you differentiate something that has a bunch of stuff inside, you need to do the chain rule. And then the chain rule is you apply this thing again with this thing here. So this is the inside of this. So just look at the chain rule of multivariable calculus. So that's where this happens. And then you get half x1. So if you do this, this term goes away because it doesn't depend on this. And then you get this, it's 2 x1t. And so the 2's cancel out here. The -1/2 means you get 1 over the square root of this. And that's this thing here. So this is how you do the math for one of those terms. And then you have to do it for each of the components. Because the Jacobian is going to be, you have to differentiate with respect to like every possible combination of input and then output. Yeah. So hopefully that's clear. Yeah. Yeah, and yeah, if you're on Zoom, we're gonna take a break anyway, so I'll try to unshare the screen so that you can kind of see the board. I don't know how many of you on like if you watch the video, like it doesn't matter if I try to show this. Like, okay, all right, okay, then this is why I try to encourage in person, but if I can, I'll try to stop sharing sometime, and then if I show the full, the full screen, then it should be able to see this. Yeah.
That right now. So like it reflects a lot in the video.
Oh, this thing?
I guess.
Maybe we'll think about it. Yeah. Anyway, this is a good time to take a 5-6 minute break, and then we'll move on to the particle filter. So yeah. And then how do if I stop share? then by make. I think this should be captured in the recording. It is recording, so hopefully that's fine. Anyway, have a good break. So yeah, we'll be back in like 4:52 or something. Yeah, yeah.
So when we like record something and we want to replicate, for example, we have a robotic hand. We move the hand, we record all the readings, like how the hand moves, which sensor, like based on sensor reading. So like do we apply filters to that and to replicate the same movement? Like what I'm sorry, filters to replicate the same movement because like uh, there were the graph was not smooth that you showed the R graph like lane is
Yeah, so we're talking about,
for example this one. Yes, so like this is similar if we record for a different robot movement. So do we
Yeah.
apply filters
Well,
and then
what's happening. All right, so what I meant here is that this is time. So maybe every second or whatever, if you have whoever is doing this picks the time discretization. So every second you get some value, and then you
on time we plotted. So
Yeah.
this graph is not smooth, but like for example, for a robotic arm, we take readings similar to this.
the reason why it's not smooth is because there's noise in the sensor reading.
Okay, so like do we apply filters to this and then replicate it if we want to do the hand actions, like perform that on the robotic arm? Again, for example, I have a drone, fly drone where I'm recording everything and I get this type of reading and I want to replicate this flying action. So do we apply
I
filter?
want to replicate. Me. I guess I kind of like, so if you're replicating something, this feels like a different problem on the state definition.
Yes, that is.
Yeah, so you could, I mean, if you want to replicate it, you could use information from your state definition, and then you have some data.
Because this has a lot of noise, but like
Yeah,
when we are giving out instructions, you can program whatever you want, right?
You, some people, if you wanted to, yeah, some people could, you could try to make it smoother. I guess if you're probably like given this, you want to replicate this behavior, you
Yes.
could always adjust how you input control to.
Okay.
Again, so this is just the result of a state estimation problem. So it's not going to be something that came out of like, I guess, inserting control. Like, well, I guess here maybe yeah, and the way I think of this, the way I think this is that that we might not have. I guess we don't. It's just some way of estimating where this robot is, and the state in the case is just like range, so like one.
Okay,
Yeah,
got it. So that is
Yeah.
a complete different approach.
it feels like a different issue from what you're talking about. Yeah, I think.
Like
If you
about like
want-
relating
if
it.
you want more equal, I think. I think comics was the more you can tracking like or other.
Yes, because like I just came up with this example, so I will try to find out more examples. Like
Yeah, I can try to find that, but which is actually something I would like to find. Yeah. Also, big word. Oh. That better? Yeah, I think it's a little bit different, so maybe that makes it a little bit easier to see. I, I, I only see, yeah, we can do more experimenting maybe next class. Maybe one more minute and then we'll get started again. Oh. Huh. Good. All right. So H is the function, so if. Yeah, this should be because H is a function here. So ZP is just like whatever was saying. I think if you're differentiating, this thing will be function H. It should be H. So the confusing thing here, yeah, we use H, but we also use HT as name at x3 comma t squared. Because H was the function that we use for linearization, but it's also the height here, so. Yeah. I think the best way to think about this is to go through and yeah, I think doing the math here is easier if we just assume x1t, x3t, but if you're thinking about the state, it's easier to think of it as x, v, h. Yeah. It's a bit of a tricky example. I'll try to avoid it in the future. Yeah, it's variables are just tricky. All right. So, welcome everyone to lecture 8 of CS 545, the introduction to robotics. So, in this lecture, so pretend we're just starting now. So we are going to be talking about particle filters. So particle filters are another filtering algorithm, and it's going to be the last main filtering one that we will discuss in this class. Yeah, so some logistics. So yeah, I kind of repeated this earlier, so just reiterating in case you forgot about it. Let me get rid of my video here. All right. So as a quick review, so recall our Bayesian network, the same one that we've been dealing with for the last few classes. So we have this, which characterizes the evolution of our control, like the robot action, the state, which are unknown, but which we want to know, and the measurements like GPS sensor, camera, or other things. And this is the assumption that we are making about the Bayes net that characterizes the system. We've made the Markov assumption on state and measurement. We've also assumed that things are stationary. So if you have the value of time t, it's going to be like whatever the same. If you change the value of time t, the dynamics will stay the same. So mathematically, that looks like this. So with the state transition probability, you have probability of xt given all the preceding stuff. You just need xt minus 1 and ut. So another way to think about this is if you look at xt, what are its parents in the Bayes net? and only xt minus 1 and ut are pointing to it. Same thing with the measurement probability. Now, a belief, the thing that we've been talking about a lot, these are things that represent the robot's internal knowledge about the environment state. So in Bayes filters, we talked about the belief. With Gaussian filters or Kalman filters, we characterize beliefs as Gaussian. So we define them with mean vector and covariance matrix. These will assign probabilities to each hypothesis about the true state. Yeah. And these are basically posterior probabilities, and I'll write out the formulas here again. Now, one thing that is kind of different for the particle filter is that the book will write out posterior over full state sequences. So instead of a single state, you think of it as a full state sequence. So there's a few reasons why the book does that. I'll try to clarify it later in the talk. So remember that a belief for state xt is this thing here. Belief of xt is equal to probability of xt given all the prior sensor reading and the action. If we have a belief for a full state sequence, then we put in 0 to t. So that goes from all the way to the beginning up to now. And then we condition it on everything here. And again, hopefully it'll be a little bit clearer later why we consider belief over full state sequence. So the motivation behind the particle filter is that we've covered various filtering algorithms. Particle filters are an alternative to these. They are non-parametric, which means they don't rely on assuming that our probabilities have a fixed functional form like a Gaussian. So Gaussians are very easy to do, relatively speaking. Like mathematically, they're often useful to if you want a closed form solution to something, but they're not useful if you're modeling something which doesn't really follow a Gaussian. And so the reason why people like particle filters is that, well, it's very simple, and it can also approximate many different types of things. Like you might not have a Gaussian for your state, but you don't need that for a particle filter. The particle filter makes very few assumptions. It just assumes that you can run a ton of samples, like maybe thousands or millions, and that approximates the posterior, right? So that's the context behind why people care about particle filtering. All right. This was the Bayes filter, so we covered that, I think, roughly 2 weeks ago. So we had the usual, you iterate through all X, you get your belief before you incorporate the measurement, and then you get your actual belief by considering the measurement. So a particle filter will represent posterior by finitely many samples. So the parametric version of the Bayes filter, where for every particle you have, it represents one distinct hypothesis. And then if you have millions of them or billions of them, then you get a whole bunch of different hypotheses. And then we have to do something about them. So, all right, so the algorithm looks like this. We're going to go through it step by step, so don't worry if there's a lot here. But you can already see that because it's a filtering algorithm, you probably expect that there's some recursion here. And you can see that here, right? You have x t minus 1. So this is the like a capital X. Like if you're writing in math, it's math cal x. And this is like, this is our representation of the belief. And then this thing at the bottom is the updated representation of the belief. Yeah, so again, it's like the Bayes filter and the Kalman filter is recursive. So it takes in the controlled and the sensor reading, and it takes in your prior belief. It's just that in this case, the prior belief is just the big xt minus 1 thing. Right. So yeah, this is the rough code, but for now, for this slide, just look at the input and then the output. We can cover whatever is inside later, but just look at the input and output. Yeah, so any questions on like the general, no, input and output? So again, this because it's recursive, it represents 1 time step. So if you're writing it in code, you would have to like put in the scaffolding for like the initial belief and then calling this recursively. Oh yeah. So before we move on to the particle filter, we should also talk about important sampling, because the particle filter uses important sampling. And important sampling is also a much more general technique. So if you've taken like statistics and probability courses, you're probably familiar with important sampling. If not, then you can learn here, then you'll be prepared for it when you eventually do take your statistics and probability. Yeah, so important sampling. It is a general technique for computing expectation over some probability density F when we only have samples from a different density G. So you have some samples from some function that maybe you know is easy to sample from, but you really want sample from this other more interesting function. So again, you don't, it's not just in particle filters where it appears, it appears in many other fields. Yeah. Yeah, so again, some distribution F that is difficult to draw samples from, which is the thing that we care about. So if you, jumping ahead for a particle filter, this thing is going to be our future belief, like our updated belief. That's the thing that we want, that's the target. But how do we get there? And we'll cover that. We'll cover why. Now you can specify some distribution G, and then you draw a sample from G, and then you multiply them with this. Like this is a weighting factor that tries to weight the distribution so that like if you sample from G, then you multiply them by this weight, you end up actually getting something that's like F. Yeah. So yeah, this is a general technique. So how does it apply to our case? Well, let's first take a look at some graphs. So first let's actually try to derive why it might work. So what's the expectation that X is a member of A? So mathematically, we can write it like this. So you have some expectation. And then inside, we have this indicator function. So this is like an indicator function that is like 1 if X is an A and 0 if it's not. Now, this thing here is just the definition of what an expectation means. So remember that the definition of an expectation is that you have to consider all possible values of X, which is what we're doing when we have the dx here. The value here is going to be like from like minus infinity to infinity, or the whole domain. This is our density function. So intuitively, it's going to be like higher in region where it's more likely that X appears. And then this is the thing that we're trying to get an expectation of. And then what happens here is, in this next line, you do the trick of multiplying by 1. So this is one of one of my favorite tricks in math. So if you cleverly multiply by 1, you can do a lot of algebraic manipulation that make things a lot nicer for you. So and then what happens here is, by doing this derivation, you get the expectation with respect to some density function g. So g is like the thing that becomes our density now. So this is a weighting term that you stick in here. So does everyone see how this derives? This is, again, the definition of the expectation, but g is now the density function, and then f divided by g is the weighting term that we have to add in there to make the math all work out. Because you can't normally just switch what f and g are and then keep the inside the same. Like that doesn't work out. But if you add in this weighting factor, it can make the math equal. I mean, it does make it equal in this case. Assuming that you have g of x is greater than 0. So yeah. So again, this is just a way to think about why we need that weighting term. So if you remember from the last slide, we said that you had to multiply by the f divided by g. That's this thing here. So we get like sample from one distribution, and then you multiply them by this weight, and then they become sample from another distribution. And visually, it looks like this. So when you have function f and g, and we would like to approximate the target density f with sample. So the way to read the diagram is that each of the vertical lines, they represent one sample. And so the density of f is higher in this region. And so you get more samples concentrated there. Yeah. So it's like if you're plotting a histogram, you get more value where it's higher. So that's what those vertical lines mean, but in practice, of course, f is very difficult to sample from. So this is the thing that we would like to get, but we don't actually have. So instead of sampling from f directly, we can actually only sample from g. Everyone see like why there's more vertical line here? Yeah, because g is higher there. Yeah. So what happens next? Like if it's easy to sample from g, how do we actually get our sample from g to turn them to samples about? I mean, if you look here, you can kind of see what's going on, right? Look at the height of these bars. What do you think the height represents? What do we mean by the different height here? Yeah, the weighting term. Yeah, so for each sample from G, multiply the weight by f of x divided by g of x. So, and then the weights are higher here. And so what happens now is we've sampled a bunch of things from G, but we're overweighting the values that are like actually far away if f is higher. So it's f divided by g. So in this region, f is very big and g is very small. So the whole fraction becomes very big. And that way, if you're doing like sampling with replacement, for example, you would sample like the items in this range much more often. So, yeah, so in particle filters, you can think of F as our target function, the thing that we want to get, but we have to compute it somehow. And G is like something that we know from the prior time step, but before we take into account the measurement update. Yeah, and so because G is like something that we already know, then it's easy to sample from, but the target is something we're trying to get, so like we can't actually, sample from it directly. But what it does assume is that you can actually evaluate it. So usually evaluating something is easier than generating a sample from it. So evaluating usually implies that you have a forward path through some kind of function. Sampling means you actually have to know like some probability distribution, then you can sample from that. But if we don't know what that distribution is, then it's hard to sample from. But in the particle filter that we'll cover, we have already computed the prior distribution from the last time step. And so we have a distribution already for us. So hopefully that intuition helps here. All right. Yeah. Got a question.
F and G, they are independent.
So you're asking, do F and G have to be independent here? No. No, they don't have to be. What you do need is like you need that G is not zero. Like if G is zero, then it's a problem. But there's nothing about like independence here. And in fact, for particle filters, F and G are not going to be independent because we're computing the target from the prior distribution. So like there's no way they can be really independent from each other. Yeah. All right. So now let's take a look at particle filters, and then we can go through some examples of how each particle moves. So this is the algorithm. I'm going to keep this for a few slides so that you can look at it more. Then we'll go through the different steps here. All right. So particle filters, I think, are easiest to think about when you have some space, right? And then there's some space where like a robot might be located. And then you're trying to localize it, find its location. And each dot in here is going to be like one hypothesis of where the robot might be. So we have some initial distribution. Xt minus 1 here. We're going to visualize that with these 5 dots. So why are we using 5 here? To make it easy to see. I mean, if you're doing it in real life, you would have maybe 1 million. Actually, probably 1 billion these days. So, oh yeah, we just have 5 here to make it easy for us to visualize it in PowerPoint. Yeah. Notationally, think of Xt as our set of samples in our current particle filter. So a given set here describes our belief. Because if you have more dots, if you have more like particles concentrated in one region, then it tells a practitioner that something is more likely to be there than others. So if this is our distribution and we're trying to interpret this, then it probably means that if we're trying to track the unknown state of the robot, it's probably somewhere here, where the dots are, or where the particles are. All right. So what's next? So what we're gonna do is there's a for loop over M. So that means we go through every particle. So every particle moves based on the transition function. So an important caveat is that the particle filter does assume that we can actually sample from the transition function. If we can't, then we probably can't use the particle filter. But we also made the assumption that we can use the transition function for the prior algorithm as well. Or like in practice, for maybe some exam question, we would just like give you the transition function. All right. So we have the set of particles. UT is some control that the robot took. So if the robot, if it's like a planar robot that's moving in a plane, then it might move this way, in which case the particle will probably move in the same direction. So for each particle, we sample its next instantiation, right? So all of these particles will independently, they will move. Now, again, imagine that this is a grid of different cells, and different particles might move to the same location, or particles from the same location might move to different grid cells. So again, for each particle, we sample the next I guess state given the transition function. All right, and then the next thing is to get a weight, right? So we need some kind of sensor reading, and then we can determine a weight. And so what we're gonna do, we're gonna assume in this example is that if we see VT somewhere, that is some location that a GPS reading might have said of here's where it thinks the robot is located. So if we have this, then the particles that are closer to this, it seems like they should have more weight, because they're probably more likely to be true. And that's what this weight means, though. Just again, think of ZT as like some kind of grid coordinate or some 2D coordinate. And each of the particles represents a hypothesis of where the robot's true state might be. So if the sensor reading says, well, the robot is probably here, then this particle should have some kind of higher weight, so the bar is higher, and then things that are further away, they have lower weight. Questions up to here? Oh, yeah, question?
The same action would be applied on the then in T plus one or at C, how does it go to two different groups? So the same action would result in the same basic same function as applied.
Okay, so you're asking if this is some grid, and then each particle is in some grid component that there's this hypothesis of where the robot's true state might be. Some particles might be in the same grid, which it might have. It usually happens when you do this. Now so the key is that the transition function is always stochastic. So there's always some kind of noise. So if you see that the robot has moved in some direction, then the particle will usually move in like the same rough direction, but there's always going to be some noise in it. So if the transitions are stochastic, which I think is true in most real life examples, then the particle might lead to different hypotheses after that. Again, if the transition function is noiseless, then I think what you end up getting is they always have the same hypothesis once they started to be at the same hypothesis. Yeah. And if you, so for if you want another example, one of the videos that I linked to on the course website, they have an example visualization of the particle filter near the end of the lecture. So you can also take a look at that too. So it's basically similar to this, but it actually shows like the grid there. All right. So here's what happened. We have a whole bunch of things that are in our set, right? But before we actually get the updated set of particles, we end up drawing a new set of particles, right? So for every single like particle like index, for every index is like some particle, right? You draw particle I with probability proportional to the weight assigned to it. And then you add this to the set. So xt is like the empty set, and then you add it. Now, is this done with sampling with replacement or without replacement? Are you aware of like what sampling with replacement mean that or without replacement? Yeah, so if you have like a discrete set of things and then you want to sample like another set from that, then sometimes you might sample the same thing more than once with replacement. If you do like without replacement, then you get an item from your set, but you're not allowed to sample from it again. Yeah. So here's an example of how this might look like. We might have the resulting 5 particles sampled like this, but 3 of the particles are like the same thing. So you can see that there's 3 different things, but that's just because like in PowerPoint, we just want to see that there's 3 things, but they really mean the same hypothesis. Yeah. So again, like actually, if it's easier for you to think of it as like a grid, then it's kind of like we might have gotten 3 things in the same cell, and this cell represents the hypothesis that the true state of the robot is at whatever coordinate this might be. Yeah. So again, think of it as like a localization problem, where you're trying to localize where the position of the robot. Oh. Yeah. And so what happened is we have 3 particles that represent the same hypothesis. And then you have 2 other particles that represent different hypotheses. Can you already see a problem like with a potential problem with particle filters? What happens if everything goes to the same hypothesis? Well, we'll see why this might be an issue. Given the time, that might be in the next Wednesday lecture. Yeah. So resample with replacement based on the updated weight. So you have 5 things that we could get, like, and because this item could have higher weight, like this is the thing that we might sample more often, or this is the hypothesis that we might sample more often. So. Then we repeat this. So we go back to the next action, which might have gone this way, and then that means our new particle might have gone this way. Again, maybe the transitions are stochastic. So some particles that had the same hypothesis, they might like go to different hypotheses next time. All right. So question on this before we go to the derivation? Yeah. So again, if you want more examples, there's some video that I linked to in the on the course website. So they have some examples of particle filters. So you could also look into those too. Yeah. Question?
How is it supposed to do I from 1 and 4?
So you said second row. a second for loop. You mean this thing? Yeah, so for m equals 1 to m. So, maybe maybe I can do something on the board. It might be easier. So, all right. All right, so if we assume that m is 5, because I have 5 different particles here, then that for loop is basically iterating from 1 to m. So it's like iterating from here, here, and figuring out like what particles to add for each time step. Now the I is indicating the particles from here, right? So maybe we can draw it like yeah, 1, 2, 3, 4. All right, so let's say that the size of the circle is the weight. And then you have five different things. And so what happens here is that the weight of W5 is much higher. And so when we sample with probability proportional to the weight, W5 is going to be weighted much higher than all the others. And so you draw particle 5 with much higher probability. So our set of particles might be, maybe we got P1, but then we got P5, P5, and P5, and then maybe a P4. Yeah. So I think the for loop is, yeah, for M is just like the index for the newer set, but I is like the index of the particle weight. Yeah. And this is what it means when we say sample with replacement, because we got particle 5 multiple times. If it's sampling without replacement, then every time we sample something, we would have to remove it from the set of things we sample from. And if we're sampling without replacement and for the same number of items, we just get the same thing, because you have to sample every item once. But sampling with replacement is very important. Oh yeah, so I got one question that says M indicates the number of particles. Yes, it does. So yeah, so M is the number of particles here. Question. Okay. Oh, if the weights are all equal, then any of the particles would be more likely. So visually, it would look like, I mean, it might look like something like that with all the weights equal. And then it's just like it would be like you uniformly sample one of those 5 particles each time step. Yeah. I mean, we didn't show the uniform weight case because it's more educational to see that what happens when you have different weights. Yeah. Yeah. All right. All right. So here's a very quick, or maybe not so quick, derivation of the particle filter. So if you remember in prior classes, we showed the derivation of the Bayes filter and then the derivation of the Kalman filter, at least for one of them. And with some simplifying assumption, because otherwise it would take like 8 or 9 pages of math, and So with deriving the particle filter, this comes back to the notion that, we're now treating each particle as a set of state sequence, as a set of sequences. So each particle is like a hypothesis, and then we consider you can consider that like all the prior hypotheses that it was like before, or I think that's one way, I think that's the way that at least that the book tries to argue for how do we derive something like this. But let's just take a look at how you would do the math here. So we have this belief over a sequence, right? And what happens here is, I mean, you've seen this trick a lot of times, right? Like you have probability of the full sequence, and then you split up the. Yeah. I mean, you can always do that. I mean, it's v1 to t, and then you just change to v from 1 up to t minus 1, and then you get to vt. So what happens here? Because like every time we split something up, we always do something the same thing to it, right? So yeah, it's a Bayes rule. So what happens here is we do Bayes rule basically to move the VT, like we convert this to that, where the VT becomes the thing that we now care about, and the probability conditioned on everything here multiplied by the probability of the state sequence. But now where we can go from v1 to t minus 1. So again, if this is confusing, just look at the normal Bayes rule formula. So you have the normal Bayes rule formula. Remove anything that you're conditioning, which is like common to all the terms. Do Bayes rule, then add in all the conditioning. As long as you're consistent and add conditioning to every term in the equation, it should be okay. Yeah. And eta is this normalizing constant. Now we also go from here to here by making the assumption that xt is complete. And what does that mean? Well, that means, oops, we go from vt conditioned on xt, and we don't need any other prior information before that. And again, another way to think about this is that vt, the only parent is xt. And this term, I guess this term stays the same. But of course, we have to do something to that term. So what do we have to do? So we split it up again. So I think this is going to be a little bit clear. So if we're trying to do something that's recursive, then we need something here that is like probability of x from 0 to t minus 1, and then with these going to t minus 1, right? So that's basically what's going on here. Yeah. And then what happens here is you get this normalizing constant, and then we split up this so that, again, just think of it as probability of a joint is by definition equal to probability of A given B times probability of B, and then everything that is common to your conditioning, you just add it to the end of every term. Yeah, so in that case, all the conditioning would be the Z1 to T minus 1 and U1 to T, 1 to T. Yeah. And then we can also assume that xt minus 1 is complete, and then that way we get this transition. And then we're almost done. So what happens here? What is U1 to T? What happens to this term? So what does x0 to t minus 1 mean? So it goes up to xt minus 1. So what happened to ut here? Ah, there we go. Yeah, yeah. Yeah. So we just dropped the t here, then it goes to t minus 1. And then we get our belief here. Yeah. So this is another way to derive the particle filter, because remember from the formula that we talked about that we had some kind of prior distribution, which is a prior set of particles. We had a transition function, and then we had a weighting term. Yeah. Yeah. So for the base filter, we had this recursive formula, and then that's also the formula that's used in the base filter itself, where you have the sum or integral if you're in continuous land. So you had our current belief, which is equal to the weighted distribution of all the prior beliefs multiplied by like all the ways that you could have gotten to the current belief from the prior based on the prior state. Like I think that's one way to think about this. Like, what are all the ways that you could have gotten from from a prior state to the current one? By prior, I mean xt minus 1 of them. The current one is xt. Yeah. And then for particle filtered, we consider the state sequences in the derivation, and then we get something like this. All right. All right, so a couple of other considerations. So particle filter, they represent beliefs as such a particle. But there's often duplicate particles that represent the same hypothesis. Because if we sample with replacement, like with the example that I just showed here, if we're sampling with replacement, then we usually get the same some duplicate item. Yeah. Yeah. And then again, we compute the particle set recursively from the prior set. And we would want the target distribution, which is the updated belief. So that's the updated belief, but we don't know that yet. But because we have the prior belief, and the prior belief will give us like just distribution, like give the particles and their, like how to sample from them. And yeah, we have that, and then that's a distribution that's like easier to sample from. So we use that and then a weighting term to make it equal to the next belief. Yeah, the next belief. All right. So in the remaining time that we have, I'm going to skip some of the math derivation and then go to some example where people have used particle filters. Then we might return to the derivation on Wednesday class. So yeah. All right. So particle filters are often used for robot localization. So again, that's the example that I was talking about earlier, where maybe you have some kind of map of the environment, but you don't know the robot's actual position. And that position is the thing that we're trying to get. But we may have some sensor reading. Now here, we're not going to assume that we have like a GPS. We may assume that we have a rangefinder reading, which that's a fancy way of saying, like, if you have a robot and then a camera that shoots a ray of light, and then you measure how long it takes to reach something and then come back, you can deduce the depth from that, like the distance, because the speed of light is the same under most in most places. Yeah, and then our state space and readings are usually continuous, so it's like a fine grid. So you might be thinking like, well, why not use Bayes filters? Well, this is a good example because if like imagine that this is like a big map of your like office or whatever, then each dot represents a potential hypothesis. And if you try to store all those in a grid or a like a discrete distribution, like it would be very difficult to do that. So instead, what we do is we store a list of particles instead of like a map from grid item to probability of being in that grid. So instead, we just have sets of particles. And then we have a list of them in memory, and then we just manipulate them. All right. Any questions on like the localization problem? So again, just imagine that we have a mobile robot like this cartoon. Well, it's like a tank, but the thing will move around and then we try to track. So I think this is a video from I believe the University of Washington. And if you look here, there's a number of particles. So they only had 40,000. Probably just because if you have more than that, it's hard to visualize it. So. All right, so samples are shown in red. So each of the red dots is a sample or a particle. All right. Then you have the number of samples. And then our estimated robot position, like this. So this might be our estimated robot position, like maybe at that initialization, and maybe we think we know the robot might be there. This is a sonar, well, it's a sonar measurement, but like it's just something that can be used to help deduce like where is the robot in the space. All right, so as the robot moves, look at what's happening to the density of the particle. So as the robot keeps moving there, a lot of the particles, they become more concentrated near where the robot is. So if you follow what's happening there, the robot was moving from like somewhere by the center and was moving in that direction. And so if it's moving straight in some direction, then it's more likely that it's in some kind of long corridor or some long hallway instead of like this area or this area. So that's why the number of particles disappears in some of the lower probability regions. And now look at what happened. The robot keeps going. So at this point, the robot has continued to like go to the right, but it has also taken different sensor readings that show like the location of different like walls that it sees. And you'll notice that it has a few different modes here. So there's one mode here, there's another one like maybe here, then there's another mode here. So again, remember that this thing here is the real robot position, but we don't know that for sure. We're just showing it here for educational reason. But in practice, we wouldn't know like where is the actual robot position. We would have to estimate it from the particle. And if we move on, then the number of particles disappears or go smaller until we get to like a single mode around where the robot is. I'll play it back one more time. And what happened here, there's only a handful of modes left, and then the robot had moved a little bit more. Oh, all right. So if you look at what happened here, I think what happens is that this might be like our most probable current estimate. But I think I mischaracterized it initially. This is probably the most likely state given our particle, but if we know that the robot had kept moving this direction and it hasn't been blocked, then the most likely state is probably like here. And that's probably what happened here. Yeah. So I think that's what's happening here. Yeah. All right. Any question? This is your standard way of like using a particle filter. Yeah.
Are the particles decreasing because you're sampling from without replacement?
So you're asking like, why are the particles disappearing? So I think what the video is showing is that it's probably saying that if you sample with replacement and then we sample like P5, like in this example, we sample the same thing multiple times, it becomes like one particle. I think that's what's going on here. So there's like fewer potential hypotheses of what we might get. Yeah. Oh, how is it possible to like increase the number of particles? Well, I think, yeah, so I think it goes back to the question of like, are the transitions stochastic or deterministic? So you could have like, two particles with the same hypothesis, but they go to different hypotheses the next time down. So I think what the number here represents is there might still be like 40,000 particles, but many of them will be duplicates. So maybe it's like showing the number of potential hypotheses. I think that's my intuition of how the video is working. Yeah.
There's a more change with
Well,
with the particles increasing.
Yeah. So are you asking like why are the particles like decreasing or? Well, I mean, I think it's decreasing because the longer we tracked it, I think once we have deduced that it's going to be like at some position, then we keep tracking it. It's more likely that it's going to be like when it moved from here to there, like we've already known, like we already have a good idea of where it might be. And then if we keep moving and it's consistent with what we know, then there's no real reason for the number of particles to go up a lot. And we're getting close to time, so we can continue the discussion after this too. So yeah. And then here's another example. I'm going to save this for the Wednesday class too, and then we can talk more about this. All right. So today we covered particle filters, so the type of non-parametric filter. So again, we've covered a bunch of filtering techniques, so state filtering to estimate the state of the robot and the environment. And then there's advantages and disadvantages. So you can represent complex multimodal beliefs, relatively easy to implement, and the disadvantage is the computational complexity in case you have to sample billions of particles or maybe trillion. I don't know. So we'll cover some of the remaining stuff Wednesday, then we'll get into the other topic we'll cover Wednesday too. So have a good day, and if you want to chat, I have office hours like right now, so we can talk a little bit more.